Okay, we are getting to the end here of chapter 8, which is gases. So last time we talked about ways to calculate the density of a gas, also the molar mass of a gas. And a reminder, we saw some specific formulas for those, but as we did sort of in the examples, it really is, again, sort of based off of the ideal gas law. So you can always sort of fall back to the ideal gas law to kind of solve those problems, kind of think of it like almost like a conversion type problem to get to the right units that you're looking for. We also talked about gas stoichiometry problems, and gas stoichiometry problems for the most part are pretty much identical to regular stoichiometry problems. Again, really at some point though along the way, you will use the ideal gas law. A lot of times in gas stoichiometry problems, you kind of use it at the end of the problem to solve for something like the volume of the gas that you produce. You could also use it at the beginning of the problem, where you would use it to get to moles instead of, say, grams to moles or something of that nature as well. We also talked about as well the idea, again, under constant temperature and pressure conditions, if you're looking for some type of volume, again, you could do sort of a volume to volume relationship in terms of stoichiometry using the idea of Avogadro's law. We talked about partial pressures, and partial pressures basically are when you have a mixture of gases that are in the same container. Each one is contributing to the overall pressure of that container, so that's why they're referred to as partial pressures. One of the sort of nice things about an ideal gas, as we talked about, were a couple of things: that the volume of the gas itself is not important compared to the volume of the container, but more importantly, in an ideal gas situation, gas molecules pretty much don't interact with each other. So there's no repulsive forces or attractive forces between different gas molecules. So what that allows you to do in a sort of a gas mixture type problem is you could calculate the partial pressures like each of the gases were sort of in the container by themselves with no other gas there affecting them. You would use the ideal gas law to do so. You just basically solve the ideal gas law for each gas separately. The volume will be the same for everybody, and also the temperature will be the same for everybody in that mixture. To get the total pressure at that point, you just add up all the partial pressures together, and that will give you your total pressure. We also saw a formula where if you maybe don't have enough information to use the ideal gas law, but you do have enough information to figure out the moles of all the gases that are present, and either you have the total pressure given to you or a partial pressure given to you, you could use the gas law there, like partial pressure is equal to the mole fraction times the total pressure. And you can use that guy there to figure out partial pressures of all the other gases, or maybe the total pressure in that mixture. The last sort of partial pressure situation that we talked about is the idea of when you do collect a gas over water, or water's involved in the collection of the gas that you're interested in, you usually will get a partial pressure situation where, in addition to the gas that you're interested in, you will collect basically water vapor along for the ride. And that creates sort of a total pressure is equal to the pressure of the gas you want to collect times the pressure of water, which is referred to as the vapor pressure of water. And this type of problem is usually used a lot in labs where you do this type of collection, where it becomes really just a subtraction problem, where the pressure of the gas you're interested in is basically the total pressure minus the vapor pressure of water. This is typically a value you can look up in a table based on temperature, and you could just subtract it off. That again gives you what we sometimes refer to as sort of the pressure of the dry gas, where we sort of remove water's contribution. It really is, in this type of collection, sort of a side product of how the gas was collected. Keys in sort of textbook type problems where they the situations occurring is, again, they say something like collected over water or saturated with water vapor. So those are kind of keywords that you have that type of situation occurring. We, I think, finished up talking about the root mean square, or the RMS velocity of a gas. And we saw a couple of things. We saw that obviously if you are looking at the same gas over a variety of temperatures, what we saw was that the average velocity does increase with the increasing temperature. which is what we would expect to happen. As the temperature increases, the gas molecules gain more energy, they fly around a lot faster, so they're moving a lot faster. We also saw that when you compare different gases, the mass or molar mass of the gas is important to sort of how fast they're moving around. The lighter gases are traveling faster than sort of the heavier gases. There actually is a formula where you can calculate the root mean square, which is this guy, and that is the square root of 3RT over M. A reminder that when we use this, the gas constant is actually the one that is the energy version of the gas constant here. And the reason for that is that relationship there, that a joule is a kilogram meter squared second squared. And what that means is that technically the molar mass, which is this guy down on the bottom, does need to be in kilograms per mole so that this will cancel out. So when we do all this, what we do end up with when we use this formula in terms of units, our meters per second is typically the units that we end up with when we actually do use that equation. Any questions on any of that stuff there that we talked about? So why don't we try one here since we kind of stopped on that. Let's calculate the root mean square velocity here of helium, and we'll do neon at say 27 degrees Celsius, and helium is 4.003 grams per mole, and neon is 2018 grams per mole. So what is the root mean square velocity there in meters per second? All right, let's take a couple minutes, see what you come up with here. I'll do it. Okay, let's take a look here. So we're going to do our root mean square velocity here, which is the square root of 3RT divided by the molar mass. So we'll do it here for helium. So we do need to convert, once again, our temperature here into Kelvin. So we'll do a 273 on that. So that should be a 300 Kelvin. Other than that, we're almost good. We also need to get our molar mass into kilograms per mole, not grams per mole. So we could divide by 1,000, which gives us 0.004003 kilograms per mole. Again, dividing by 1,000 there to do that. The reason for that is, again, this is going to be 3 times 8.314 joules per Kelvin per mole times our temperature, which is 300 Kelvin, divided by our guys here in kilograms per mole. And that is because the 8.314 basically becomes kilograms meter squared, second squared, Kelvin, and mole. And that again is the joule part of it there. And again, 300 Kelvin. As you can see, the number doesn't change, but that is how the units do cancel out. Again, the kelvins will cancel, the moles will cancel, kilograms will cancel, and that will leave us meter squared over second squared, which becomes meters per second, obviously, when we take the square root of it. So if we do that there, we get 3 times 8.314 times the 300 divided by 0.004003, and a little square root action on it. Gets us something like 1,367 meters per second would be the root mean square velocity there of helium. Any questions on that calculation there? Once again, we'll do the same thing here for neon. It's going to be the square root of 3 times our 8.314. Once again, I get rid of the joules here. So that will be kilograms meter squared second squared, Kelvin times mole, our 300 Kelvin, which is our same temperature. And again here, taking the molar mass and converted it to kilograms, which would be divided by 1,000, as there's 1,000 grams in a kilogram, which is why we're dividing it by 1,000. Gives us 0.02018 kilograms per mole. Once again, kilograms canceling, Kelvin canceling, moles canceling, leaving us at meter squared, second squared, and we end up with square root it. About 608.9 meters per second. Any questions on that calculation there? So we see here helium is, approximately moving about 3,000 miles per hour, and neon is moving around 1,300 miles per hour. We could clearly see here helium is moving a lot faster, and it is because it is a lighter gas, obviously, than neon. And if you think back to the partial pressure problem we did with these two here, if you remember, the partial pressure of helium in that case was something like 12.7 atmospheres versus neon's like, I think it was it 2.4 maybe atmospheres it was. And again, this is why here we could see it moving, about 2.5 times or so faster than neon as it's moving around. So causing obviously a lot more collisions and a lot more contribution to the pressure of that mixture. Any questions on that there? Yeah. Next thing we're going to talk about is what is referred to as gas diffusion. Gas diffusion is the gradual mixing of molecules by virtue of their kinetic properties. So we got two kind of containers down here. One is NH3 and one is hydrogen chloride or hydrochloric acid. And when they do come together, they make ammonium chloride, which is this white that you kind of see there. This should go with a different color than blue. That's here. So this one, a white cloud that we see here is the ammonium chloride as they mix. So what we see here is the mixing actually is occurring much closer to the hydrogen chloride gas or the hydrochloric acid over here. The reason for that is what we basically just talked about when we look at the molar mass of NH3 versus HCl. Without doing the calculation, we would expect the NH3 to be moving a lot faster than the HCl because it's lighter. Because it's lighter, it's going to move a lot faster. And that is why when this guy comes out and this guy comes out, we see the mixing occurring closer to the slower moving gas because the NH3 is able to basically get over there a lot faster than the HCl is leaving the container. You can actually calculate a couple of these things here if you're interested in sort of the rates or the molar masses of guys. This is R1 over R2. These are rates. So, how fast something's moving, say per second, per minute, per hour, something of that nature. This is the molar mass of these guys. And this molar mass is in grams per mole. So we can do the molar mass like normal over here for each of those guys. So M2 is obviously the molar mass of the second substance, M1 is the molar mass of the first substance, and R1 is obviously the rate there of the first one versus the second one. Now, gas diffusion is that sort of mixing as that one guy goes from one side to the next, basically based on their sort of how fast a gas is moving versus another. There's also gas effusion. Gas effusion is the process where basically a gas under pressure will sort of escape from one side of a compartment to the next through sort of a hole, if you will. So obviously we have a lot of gas molecules in here, a lot of pressure, small little hole right there. So these guys are going to pop out through the hole kind of to the other side there. And we could also sort of calculate it, very similar sort of equation there that we just saw. So once again, R1 and R2 are our rates, M2 and M1 are our molar masses, and here T2 and T1 are time, so time 2 and time 1. So if you know sort of how fast something is moving versus something else, you could do these type of calculations. So if we look at a problem like what we have here, we have two gases. We have a nickel carbon oxygen type of gas here. And under the same conditions, we see that methane, which is CH4, effuses about 3.3 times faster than this sort of nickel compound. So we could use this sort of formula to help us understand or figure out what the actual compound we're dealing with is, since we know how it basically compares to methane. So if we take a look at this here, we have our basically R1 over R2 is equal to the square root of our molar masses here of our first and second compound here. And it was 3.3 times, right? Yeah. So we have a nickel compound here, and we don't know what that is, but we do know that CH4 effuses 3.3 times faster than this guy. So if we call our first guy here, M1, the methane, we'll call our M2 the nickel compound there. Doesn't really matter which one you pick, as long as you kind of keep those guys together. The first thing we'll need is the molar mass of our CH4. So that would be 1201 plus 4 times 1.008. And that would get us 12.01 plus 4 times 1.08, 1604 grams per mole. This is actually what we're looking for, since we really don't know what X is at this point. We could use this formula to figure out the molar mass of this compound. So since I called M1 CH4, that means that R1 would be about CH4. And what it said was it was basically, this guy would be this guy here. Said that basically this guy is 3.3 times faster than R2, right? So this would be R2. So that's everything that we need here to go into our formula. We would take basically 3.3 R2 divided by R2, and that would be putting those guys into here. Would equal the square root of my M2, which is my nickel compound, which is what I'm looking for, divided by the molar mass of my CH4, which is 1604 grams per mole here. Any questions on that setup there? And again, the top part here, 3.3 R2 is what R1 would equal, because it's 3.3 times faster. Although we don't know what R2 is, we do know it should be the same number, so those guys should cancel. And that means that we end up with 3.3 is equal to the square root of M2 divided by 1604. To get rid of the square root, we're actually going to square both sides. So if we square both sides there, that's going to be 3.3 squared, gives us 10.89. When we square root the right-hand side, we just get whatever's left in the square root there, 16.04 grams per mole. We're going to multiply to 16.04 to the other side. And what this gives us is approximately, we'll call it 174.7 grams per mole, would be the molar mass here of really our nickel compound. First off, any questions on that calculation there? So you may be asking yourself, how does this help us sort of figure out what this compound actually is? When we look at the formula of this nickel compound, the one thing that we for sure know is that there is only one nickel, right? There's definitely just one nickel in there. So we know that if we take the molar mass of what we just found and we subtract off the molar mass of nickel, which is 5869, basically nickel, that will give us 174.7 minus 5869, gives us about 116.01 grams per mole. That 116 grams basically is made up of these guys, right? And we know basically we have so many units of the carbon and oxygen together. So since we know inside the parentheses there's one carbon and one oxygen, we know that if we take the molar mass of both of those guys together, 12.01 for the carbon plus 16 for the oxygen, means that every CO unit is equal to 28.01. And we have so many of them, which equals 116. So if we take the 116 and divide it by 2801, we end up with approximately 4 of those carbon oxygen units, which means that should be what X should equal. And our correct formula here for the nickel would be NiCO4. You get like 4.1, but we'll round to the nearest whole number in this particular case. So by using the information about how another gas effuses, we're able to figure out the molar mass of this sort of unknown compound, and then sort of doing a little bit of calculation here, basically able to figure out the actual formula of this unknown compound. Any questions on any part of that there? So gas diffusion, basically the mixing of two gases based on how fast one is moving in terms of their velocity. Gas effusion, again, is sort of that movement of a gas molecule from one compartment to the next through a small opening as fast as they effuse from one side to the next. Any questions? Both kind of the same sort of formula. Obviously, as well, you can use times instead of rates. If it took like 5 minutes for one, 2 minutes for another, you could kind of use that as well. Any questions on that there? All right, so the last thing we're going to talk about here is deviations from the ideal gas. Remember that we talked about last time, and in most situations, we deal with ideal gases, and basically the two sort of main things that make something an ideal gas, as we talked about, is the idea that the volume of the gas itself is sort of thought of as being negligible or sort of zero in comparison to the container at which it's in. You think of it as, you got like a small little like jelly bean in a big bucket, right? The actual volume of the jelly bean versus the volume of that big bucket, not all that important. It's sort of negligible based on the size of the container it's in. The other thing that makes something an ideal gas, as we talked about, is there's no attractive forces or repulsive forces between gas molecules. And again, as we talked about, that is why in those kind of mixture problems, we could assume, again, that they're sort of in there together. And under normal conditions, which is really where we deal with most of the time, this is sort of how gases behave. Even in sort of non-normal conditions a little bit, they still, for the most part, will behave relatively close to an ideal situation. And it's a lot easier to assume an ideal situation. But when we do get to really high pressures or low temperatures, like really low temperatures, so high pressures and low temperatures, we do start to see some deviation from this sort of ideal behavior. And the idea of that is we get a situation which is sometimes referred to as real gases, unlike the fake ones we talk about. These are sometimes referred to as real gases. Well, under these really high pressures and really kind of low temperatures, we do need to take into account actually both of these things. So under those conditions, the volume of the gas itself does become sort of relevant to the container it's in, and the attractive forces between gases does also come into play into that. And that's what we see if we take the ideal gas law and solve for the ratio of PV over RT, in an ideal situation would equal 1, which is what we see here. But as we start moving in terms of really high pressures, as we see here, we start to see a lot of deviations here from an ideal behavior. And that takes into account, again, those attractive forces and repulsive forces that do come into play under these conditions. So why do we sort of, in the most cases, think of gases sort of in an ideal situation? The reason for that is under normal pressure, We talked about what normal pressure is, and normal pressure is pretty much like 1 atmosphere, which is like way over here. So way over here, even outside a little greater than 1 atmosphere or so forth, they're still, for the most part, gases still behaving pretty ideally. But obviously, as you travel, 100 atmospheres, 200 atmospheres, that's some serious pressure happening here. We get a lot of deviation that occurs. So that's why under normal conditions, a lot of conditions, we sort of assume ideal situation because, even outside of 1 atmosphere, it's still going to relatively behave ideally. It's not really until you get to those really big pressures that you start seeing a lot of deviation sort of occurring. So let's talk about what happens when we do get some of these deviations that occur in an ideal versus sort of a real gas situation. So real gases, like I said, do not behave like ideal gases at high pressures or low temperatures. And again, those are the two things from the kinetic molecular theory of gases that we talked about that basically makes something an ideal gas. So at low temperatures and high pressures, these assumptions are not valid. So let's just talk about really like those two situations. When we have low temperatures, our gas molecules are going to be moving faster or slower? At low temperatures, gas molecules should be moving slower, right? Which means under those conditions, as they pass each other, they're moving a lot slower, which means they are going to be near each other for a lot longer period of time, which means there's probably going to be some interaction that's going to happen, as opposed to an ideal situation where maybe they're moving a lot faster and they're not by each other as long. So we are going to get that sort of attractive forces or repulsive forces coming into play under those conditions. When we think about really high pressures, right, pressure and volume, right, is like Boyle's law, and it's an opposite relationship, right? So if the pressure goes up high, the volume goes really low. And when you got an extremely high pressure, that means you have a very small volume, which means by default, those gas molecules will also be super close to each other, right? They're in a very small space. There's not a lot of room to move around. That also will keep them near each other for a long period of time as well, which will basically keep them interacting with each other. So under these conditions, it really kind of puts all the gas molecules near each other for a lot longer period of time than we would see in an ideal situation. And that's again in a real gas situation where we do have to take these into account. So because real gas molecules do take up space, their molar volume of the real gas is larger than is predicted as well. So again, in sort of a real gas situation, say versus an ideal gas situation, we got the gas molecule in there in an ideal situation. So it's relatively small versus its volume. But under these sort of extreme conditions, we got like, very small volume. So the space that's basically going to be occupied by that gas molecule is going to be significant in that situation versus, again, in an ideal situation, because it's very small in terms of the volume. And that's what we see here. We see that in an ideal situation, which is our sort of reddish line, it does basically hang on ideally, but as we start building up those pressures, we actually see that it actually becomes a little bit lower than what we would expect in an ideal situation. Sorry, a little bit higher in a non-ideal situation. The ideal is a little bit lower in that graph, the molar volume, which is our 22.414 number. So the effect of molecular volume at these high pressures, the amount of space occupied by the actual gas molecule, again, is significant. So it's like, again, taking a golf ball that's occupying, like this container maybe, versus, a golf ball that's occupying a big giant bucket. And again, it's going to take up a lot more room, and you got to take that into account. So our good friend named van der Waals took that into account. Van der Waals did a lot of work with, as we'll talk about in the next chapter, sort of intermolecular forces, how molecules interact with one another. And he basically comes up with what are sometimes referred to as van der Waals coefficients or factors. And there's A and B. And A and B are van der Waals constants. And they are specific for different gases. And so you would have to go to a table and sort of look up these values for different gases. And basically, he did a correction to the volume as a result of this really high pressure situation. These are all our same guys from the ideal gas law. That's our moles, that's our gas constant, that's our temperature in Kelvin, that's our pressure in atmospheres, that is our moles, and then this would be obviously our van der Waals constant for B. So this is sort of what he did is, as we'll see here at the end, is he took the ideal gas law and sort of built in these sort of corrective values for real gases. And the other sort of thing, again, that's affected is by temperature. So because real gas molecules do attract each other, because they are near each other for a much longer time in a real gas situation, the real gas is smaller than predicted by the ideal gas law here. And that's, again, what we see here as we get temperatures starting to drop a lot here. Remember, absolute zero here is 0 Kelvin. So we're getting into that negative Celsius sort of degrees as we come down towards 0. We start to see some separation. So van der Waals as well took into account the attractive forces that occur. And because the attractive forces occur between molecules, it does affect as a molecule is moving around in a container, as I might have drew last time, if there was some attractive force to it between these two molecules, it would prevent this guy maybe from hitting the container as fast as it normally would. It would sort of slow it down, and that would have an effect on the overall pressure of that situation. So van der Waals constant A takes into account sort of the correction value there for pressure. And once again, these are all of our normal ideal gas law sort of guys here with our van der Waals constant there happening. And that's, again, what this thing shows, the effect of intermolecular forces. Again, if this molecule is sort of attracted to other gas molecules, that's going to sort of slow its flight, if you will. And again, going to cause perhaps maybe less collisions occurring and affect the pressure. So this is van der Waals equation here for real gases. And it is basically the scary version of the ideal gas law here. So this is our PV basically is equal to nRT with our correction here for our volume and our correction for our pressure in this case. Everything in here are the same units that you would use in the ideal gas law. So pressure, again, has to be in atmospheres usually. Volume, once again, should be liters and should be moles. Obviously, temperature should be Kelvin. R's are 0.08206. Again, A and B are values that you can look up for a table. And as you see, it is specific for different gases. So depending on the gas you're dealing with, you will have different A and B values for those different gases. Depending on the table that you look it up with, you do want to make sure you watch out for units. Sometimes if you look up a van der Waals constants for these guys, there'll be some weird units sometimes in there. So you want to make sure, again, you get everybody kind of into liters and atmospheres and stuff like that. Why do we sort of, again, use the ideal gas law, which is PV equals nRT there on the bottom, versus maybe the real gas law here, or van der Waals equation? As I mentioned before, most of the time, like on that graph that we saw, we're dealing somewhere in the, the 1 atmosphere sort of situation. And even, again, for slightly higher than that, maybe slightly lower than that, most gases will still behave under the ideal situation or pretty close to an ideal situation. And when we look at the ideal gas law, which is this bottom one, it is frankly a more universal gas law, because you could use it for any gas you like. The van der Waals equation is really a more specific gas law, because you have to go look up the A and B values for the specific gases you're dealing with. And obviously those A and B values will be different depending on the gas that's there. So a lot of times we do sort of assume in most situations, the ideal situation, because it is a little bit more universal to use the ideal gas law in those situations. But if you do have extremely sort of high pressures, really low temperatures, you really should use the van der Waals equation. Again, you do solve it pretty much like the ideal gas law. except you got to look up those values. Obviously, those values would be provided to you, obviously, if you needed them for everything, an equation or something like that. Any questions on real gases here? Any questions on gases in general? So that wraps up the gas chapter here.